Elizabeth. Good to see you here. Who's all here in the chat? If you have questions about the project, it is time for project time. What questions are there? Who is working on the project? And what questions do you have? I've got the project here ready to go. We did some decision trees during office hours today. We could talk about the executive summary. There were questions about one sample and two sample T that we didn't get to, but it's open floor for questions right now. Ask your questions. Let me know, and we'll work on said questions. Been working on today's quiz, and I keep missing the question about store A and store B, getting the wrong T statistic and p-value, but I'm using the site you gave. Do you want to do that right there? Elizabeth, we can work on that. It's anyone's call right now to work on anything. We've sent out the review list for the project. So Elizabeth, if you're here and you're 201, your questions are first in line. So let me get my Pearson up and going right here. And this is a quiz question for two sample T's. Remember, if you're working on anything right now, 201 gets complete. This is like 201 office hours only. But no, if you're 474 and then we run out of questions, we do your questions. 474 is going to be like, wait, what? Oh my God, these things look so different. I do not like these new colors for my Pearson. What have they done to us? They've changed how my Pearson looks, and I don't like it. It's change, and it looks different. So let me get the store A, store B question up and going here. And one moment. There are different orders for me. Small glass, large glass. It's just, I've seen something I've never seen the way this looks. Here we go, store A, store B. Okay, we got the question up and going, and if you have more questions, let me know. Let me close out of this chat here, bring up our chat. Yeah, I know, right? They just like did this over the last few days. So yeah, I've clicked an answer. Let's hope it's the right answer. But that one's the right answer. Let's do this. Let's check out the store A versus store B. Here we go. So do customers spend more on trips to store A or store B? Suppose researchers are interested in this question, collected a systematic sample from 80 stores in A and 79 stores in B. There's the sample sizes. Customers by asking customers for the amount of their purchase at the stores. The data collected is summarized by the accompanying table. Suppose researchers decide to test the hypothesis that the means are equal. So what should be the alternative then? The degrees of freedom formula gives this many degrees of freedom. Test the null hypothesis with an alpha level of 0.05. More on that in a second. But if they want to test to see if things are equal, like there is no difference, because that's what we're looking at here. The null would be that there is no difference between store A and store B's means. This means like how much on average people spend at store A. If we subtract that from store B, we would expect to see 0. So that's the null hypothesis. A lot of these have the same null, but then not equal, great job, Elizabeth, right there, is going to be the alternative. Now, it wants us to get the T statistic right here. So let's go ahead and grab our data table. And with the data table right here, we're going to go over and make the T statistic. Okay, T statistic, ready to be made. To do the T statistic, we need the following. We need to go ahead and just go off the screen. To do the T statistic, we need the formula. You will be given these formulas on the test, and the formula is the T statistic with degrees of freedom given to us by the problem is equal to y bar 1, which is the sample mean 1, minus y bar 2 over square root s sub 1 squared over n 1 plus s sub 2 squared over n sub 2. So we can start plugging in our numbers right here. They give you all the numbers. And I'm pretty sure they did it A minus B. Make sure you do it in the order they did it. They're doing A minus B. Very important right here. We subtract them in the way they want, or we'll get the negative positive version of our T statistic. So we're going to take just the y bars, which are the sample means. And there we go right there. It's a difference of 7, or rather negative 7. And then we're going to go square root. We're going to square these values right here, 21 squared. We'll do that in a moment. Plus 19 squared. We have to keep those with the right ones, not constant sample size. And so we'll solve that bottom here in a second. The top of the equation, parts this over here, negative 7. And the bottom of the equation, that's 45 minus 52 is negative 7. And the bottom of the equation is like 400. What is this? 441 divided by 80 That's 5.5. That's what that is equal to. 19 squared divided by 79. And that's 4.5. We add the two together. We get 10, and we square root it. Be very careful. If you're getting numbers very different from mine, there's going to be an error. Can you tell that the t statistic right now is going to be a little bit bigger than this number? So my t statistic right now is going to be, just think about the way these numbers work. And when you think about the t statistic, we'll just put an arrow. So can you give an example of 1 sample t and 2 sample t? Yeah, let's do that next year, Mary. You got it. Thank you so much. Excellent work. People are doing excellent work. And let's go ahead and copy this. 7 divided, it's negative this, negative 2.204. And that's because the negative is right here. So just make sure to divide these out and get the number you're looking for. So this is the t statistic, and it tells you how far these numbers are away, because all we're looking here is at the distance. These two numbers are apart, and then we're standardizing this distance right here in terms of standard deviations. So how far are those numbers apart in terms of standard deviations? And they're 2.204 standard deviations apart, standard errors to be very technical. Still the idea of standardizing the values. And yeah, that's got the first part done, 2.204, and it's negative because of the way we did it. So let's drop this into here. Now the next part, which is a little trickier, hopefully we do everything correctly, cross our fingers. The new MyPearson, they're going to be mean to us. We need to go and get the p-value, so we need to go to a t-applet. Now, if you're off by the tiniest amount, please tell me. This t-applet should give enough decimals, 3 decimals. So the t-applet right here, Mubot's going to help us out. Mubot, where are you at? Oh, Mubot, are you not awake? Oh, he is awake. Good job, Mubot. Thank you, Mubot.
I am Mubot.
Chill out, Mubot. So here we go with the t-applet. The t-applet is going to show us the t distribution, which is that value we just found here of 2.204. Now, what's really interesting about this is we need to put in the positive or negative version of this, because Applet doesn't like that extra number. So the reason we're doing the positive and negative version of this is because we're doing absolute value. If we did a greater than test, it'd be to the right. A less than test, it'd be to the left. And the absolute value is the two-tailed test. Greater than or less than in terms of absolute value. Less than test, greater than test, does not equals test. Very important to know each one of these. We need to put in our degrees of freedom, which is going to tell us which t we are using, 155.82. So 155.82 degrees of freedom. And then this gives us the specific t distribution we are using for this question right here. So we are using a t with 155.82 degrees of freedom. We should be all right. It didn't let us enter that last decimal. We get a p-value of 0.029. I think we've entered in enough decimals. We should be good. I always get worried when the applet doesn't let you enter in everything, but it says 3 decimals, and we've got 3 decimals on the screen. I think we're okay. And this is the reason, once again, we are doing the two tails is because we have the does not equals alternative. Had we selected this right here, we actually need to make sure we're putting in the negative then. If we had selected the greater than to see if there is a larger mean between the two, we would do the greater than. If we had selected the less than alternative, we'd go over here and we'd be selecting this one. If you look at points to the left, which we're not doing, but this one right here would equate to graphing it like this because we're going less than the t statistic. But we're doing the does not equals, which is simply double, and it's some decimals we don't see in the background, but we're doubling it right there, and a little due to rounding, we don't get the exact double. So hopefully that makes sense on how we're getting this p-value right here and graphing it. But I'll pause right here and let people solve the last one, because this is where it gets a little bit easy, and I love it. Like, this is the greatest part about the test. What do you notice about this p-value in 0.05? When the p-value is low, we always do this. So what do you notice when the p-value is low right here? What are we going to do? So it should narrow it down to between two choices, because the p-value is low, something, something. So your p-value here is low, so you should be like, p-value is low. Brian says when p-value is low, something, something. Reject the null. So when you reject the null, you're saying like, I don't think the null is true anymore. So that means you have evidence for the alternative, which is evidence for them not being equal. You're like, I reject that null. There is evidence for the alternative. Great job, Elizabeth, right there. Let's go ahead and check our answers. Woo! I promise you, I even get a little scared sometimes. You carry a decimal wrong. You don't enter everything in the right way. Is that making more sense right here, Elizabeth, on how we're doing this, how we're getting these numbers, just solving out, getting the t-statistic, getting the p-value, and being able to... A decimal error will... Everything will go crazy. But really good, kind of tricky question. Goes through and uses the equations. Go through and mark your notation. Make sure you have right here your standard deviations. Square them over the sample sizes. Yep. Just very carefully solve it, and you should be good. But I've made errors. It happens. Awesome. Let's go talk about a one sample t-test to begin with. Look at that output and do some interpretation. Here we go. Okay, Mary, great job. And everyone working on the projects, great job right here. We're going to go look at some one sample t-test to start, and then we'll do some two sample t-test project related work right here. Okay, one sample t-test. Here we are. One sample t-test. Okay. Time to do one sample t-test. I tell this for future Brian. Create a one sample t-test. Include the output showing the distribution with the summary statistics in one picture. That's a requirement right there. Also include in a separate picture the confidence interval. Choose any % confidence. That's second. Can you go over question 4? You bet, Mary. We'll do that one next. You got it. Do you want me... What would you like? You've got the floor here. Would you want two sample T after this, or the question 4 on homework 19, which is going to be some chi-squared? Your call. Pick which one you want. We'll do that next after this. Finally, include a value your company wants to test as a hypothesis. Interpret to the reader the confidence interval. I'm just putting numbers by the requirements. Next, explain to the reader the results of the does not equals test. Oh my gosh. Finally, explain how the confidence interval and the test results come to the same conclusion. 6 requirements on the screen right now. So let's go ahead and kind of look at this right here and do an example. I'm going to switch data sets maybe, because I don't want to do all from one data set. Let's hop over here to the donor data set, because we did one from the student earlier. Okay, donor data set. This is donors to a campaign right here. Let's take a look. Let's see right here. Trying to think right here. Median home value is interesting. Are these like really rich neighborhoods? Because if those are thousands of dollars, it's like a median home value of $3.4 million. And donor ID. Median home value. I don't know. Okay, let's see right here. Account age. Those are all the same. I don't love this data set for this question. I picked a data set I don't really like. Response rate percent. I don't love this data set. I'm going to go a different data set. Let's go to the diabetes one. Here we go. Different data set. And let's look at people's blood pressure. And what do people think this is? Is this diastolic or systolic? If you know anything about blood pressure here, I would highly doubt this is one of the two. Go to descending. If you look at these numbers and you know something about blood pressure, 120 over 80 is considered pretty good, unless someone in the chat says I'm way wrong. And what? How can you have a blood pressure of 24? How could you have a blood pressure of 24? You can finish project then. Okay, I'll do that order. You got it. I do not understand. That seems weird right there. I do not understand. This person has they're 21 years old with a blood pressure of 24. That something going on there. All these ones right here, I question this data set at this point. But this would have to be diastolic because none of these numbers get anywhere near systolic unless you're talking about like the 100. So I think they're collecting the diastolic, which is when your heart's not pumping, this right here. And 80 is a good number to test. So let's see if there is evidence right here that people have a diastolic different than 80. So we're doing a one sample t-test right here, which is one quantitative variable. One sample t-test is one quantitative variable. We're going to go to Analyze Distribution. And under Analyze Distribution, we're going to double click our variable. And you notice here it's quantitative. Mr. T, quantitative variables. He's mean. I'm sure he's a nice guy. But Mr. T, I like to say, is mean because T is for quantitative variables. And so we're doing one quantitative variable. We're doing a t-test, t-interval right here. And so we can see the distribution looks pretty normal. We like that. A little bit of outliers down there. There's our person with that 24 blood pressure. Let's go here to top and go to table and stack. Put it in nice horizontal format. Does it for you. I like to increase my graphic size, kind of give a little full screen to it right here. And then we get a lot of the output we need. And we're going to test the value of 80. Testing the value of 80 right here can be done by going to the red arrow and going to test mean. So this is where we're doing a one sample t-test right here. Now I want you to think about something for a moment. I actually know that we're going to reject this value. How do I know that we will reject the value at 0.05 alpha? And I already know we can reject 80 and say that the diastolic, which is said blood pressure. If you call it blood pressure, that's fine. I can already reject the value of 80 and why? Because I've kind of gone to the last question right here. How do I know I can already reject the value of 80 for the does not equals test? How have I already concluded that by looking at my output? So I'm going to go here and test it in a moment, which we need to put this output on there. But how did I figure out already that I can reject the value of 80? Here's a hint, because I'm 95% confident what? The true value of blood pressure, the true mean for all of these individuals, the true mean, like if we took for the full sample of individuals, or not the full sample, the full population of individuals, if we had all the data, I'm 95% confident that it's between what and what. That's actually a confidence interval there that you can use. So I'm 95% confident that the true mean of blood pressure is between 69.4 and 71.9. So when you think about testing the value of 80, if I knew how to type 80 is well outside of this interval right here. 80 is well outside. 80 is like far, far outside, which means we are going to super reject that value. If you look at where we are by assuming 80 is true, we observed a value at 70.66, which is way far away from it, which when we look at the test right here, we reject it with a very, very small p-value, which is less than 0.05. So we're saying right here, we have strong evidence to reject the value of 80, given that we observed 70.66. That's what we saw for this sample. If you look at where the mean of this is at, the mean of this sample is about at 70.66 when you average all the values together. And so our observed value right here of 70.66 is so far away from our hypothesized value that if the hypothesized value is true, we would see values around it, but we don't see our value anywhere near this. Our value down here is super far away from it. Can we use our prompt executive summary? Kind of. So great question right there, Emmy. Here, I'll go over that next right here. And yeah, so we'll do that one. Then we'll hop back to Mary's question. And then, yeah, I can go into some specifics. I cannot speak today. Specifics on that. And yeah, so going over this output, this is the output you need. But think about how you're going to interpret this with I am 95% confident. The true mean blood pressure of these individuals is contained in the interval blank to blank. Think about what we're testing right here. We're assuming that this is true and we can reject it. We have a lot of the output. Let's go do that question right here. So the question is, can we use our prompt executive summary and stuff from project one? Let's go check that out right here, right now. So there are some changes to this project. So when you think about the prompt, and you don't need to include the prompt because I can see it, like you want to think about this as a report to a company, which a lot of great job on project one. If you got a great grade on project one, you're doing things right. If you didn't, please ask questions. Like if anyone like didn't get a great grade and you're like, hey, I didn't get a great grade. I got like a 70. Look over your notes where you lost points because I put some notes on everyone's projects. And the biggest thing you're going to notice right here, what is really going to have to change if you're using the same data set? So Emmy, if you're using the same data set, what is really going to change in your executive summary? What is really going to change in your executive summary where you need a lot of people lost points in their executive summary because of this? What is going to change? First, you're going to outline the problem you're dealing with. That might sort of be similar. I could see how that could be the same. But next, you're going to go over the results in the report. So the question becomes, do you have the exact same results in your report as last time? And the answer would be no. So your executive summary may start out the same, like we're very interested in analyzing diabetes and the characteristics that go into it to help people make better health plans here at our company, blah, 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 blah. So you could start out very similarly at the start, but then when you go into the summary of results, then you're going to have a different summary of results. But then finally, your action item at the end, what decisions do we make? Since this is going to be based on your findings in the report, your action item at the end will actually be different. Does that make sense, Emmy? That your action item at the end of this, what decisions you make are going to be based on what you're doing in the report. So it would seem as though, and it would definitely make sense, that your suggestions this time, make sure they're well connected to the report. That's a big thing right here. Some people lost points on their action item because they said like, we're just going to, yeah, awesome. So yeah, just think about, don't worry, as long as you connect it, I'm not going to be like, I disagree. As your manager, boss person, I disagree. You want to make sure you just give numeric findings, and we don't need the graphs from the previous. Exactly. There's a different project. We got your previous project on file. Excellent work on that previous project. We've got it on file. We can pull it up if need be. You don't need to use the previous project's graphics and everything. This is like your second project you're doing for the company, doing a little more advanced analysis, and you're going to go through and kind of, you can state, the problem can be the same, like the opening to the executive summary could be the same, like this is this company, our interests are this is what we're analyzing, and then the results are going to be, it's basically separate, exactly. The results are going to be different, and then your final bit about what you're going to do is going to be different. So make sure for your opening, you could use the same for the first part of the executive summary, like the first 2 or 3 sentences. Then your summary of findings needs to be based on what you found throughout the report here. And then your action item is going to be based on what you learned from this report. So it can have similar themes, but you can't just copy paste the last one. Does that make sense? So hopefully, I'm going to be fearful when someone copy pastes their last executive summary. We're like, no. But no, great question right there. Let's throw out some 50 points. So we're going to make Emmy a mod too. Being adventurous, making people mods. Usually I reserve this only for class time, but our class doesn't meet in person. Well, I mean, like, we meet here, but we don't, everyone knows. We're asynchronous. Emmy, you're a mod now. Awesome. Got those mod powers. So let's see. I think there was 2 sample next. Mary was interested in 2 sample. Let's hop back here to Spice. And keep asking those questions. We got 2 questions ready to go right here. We're going to do the 2 sample, and then we're going to hop over and do the chi-squared next. But if you have a question, we definitely have more open questions after this. So ask those questions. Sometimes I might kind of have someone jump the line, especially if it's a little quick question. But we try to do as many as we can. What does it mean to be a mod? So every once in a while, we'll answer that real quick here. Every once in a while, because these are public streams, sometimes random people will just join. And they'll say something that we're like, we don't want you saying that. And we can easily just remove someone's chat from the stream. So having mod powers means you have the ability to block people, ban people, stuff like that. The best way when dealing with random people on the internet just trying to be not nice on streams, we had someone a few days ago actually just attempt that, and I just went, hide user on channel. Didn't reply to them, saw their comment, read it, and you're gone. I don't know. Since we're here for education, and we have some fun. Like if someone comes in, it's like, hey, is this stats? Like, yeah, this is stats. Someone comes in. And he's like, another 50 points for me right there. Yeah, and then one time I had a student like removing chats from other students, and I was like, don't do that. So and I almost was about to remove their mod powers. And we're always here to be respectful, kind to others, civil, and that's what we do. Is it's all about respect. It's all about civility here on Stat 201, and 99.99% of the time we achieve that goal. And it's really the 0.01% is because a random person on the internet wants to be random internet person, and whatever. Psst, we don't care. We move on. We have a good time here, and that's what I like. And everyone stays really positive and supports us. So thank you for swinging by if you're here just chilling out. Because we do get some random people. We've got a gentleman from Bulgaria who's a doctor who comes by and talks some stats. It's really cool. We have a Cincinnati Stats comes and visits us. Calzone Tyrone, I love it. He will appear. He might be here for one of your Kahoots. He visited our first Kahoot we ever did, and he's from New York, and he was taking statistics in New York. He saw a Kahoot for statistics, and people actually like sent him the code, so he joined in because we didn't show the code online at that time. So they actually sent him the code, like I think he was like someone sent them their Snapchat or something, and it was not things I would be just doing randomly on the internet, but they got him the code and they got him to join, and like I think people like actually like started like made a friendship out of it. And that's good. I'm glad we can pause it. I'm glad it's not like a weird thing, but I was just like, that's crazy. And that's how Calzone Tyrone became one of our top Stat 201 members. And he's also a mod on the channel. I modded him. He came here enough and interacted enough. It's rare that I mod people who aren't students, but, you know, come here for a long time and interact and are positive. Eventually you earn my trust. My students have my trust instantaneously unless they start removing chats, what they shouldn't do. I was like to students, I was like, don't do that. Don't do that. Don't remove other students' chats unless there's something bad, or I'll deal with it. But anyways, let's do a 2-sample t-test. We'll get serious here. Put on that serious face. Let's do this. 2-sample t-tests. When we do a 2-sample t-test, that's future research. Go away, future research. We don't want you here. So 2-sample t-test. A little less to do this time. Perform a 2-sample t-test. Well, that's a task in and of itself. Explain clearly to the reader the point of the test you are performing and why it is of interest or important to the company. Without using statistical notation, explain the null and alternative hypothesis. So don't write statistical notation. Next, interpret the results of the does not equals test to the reader, which we were doing one of those earlier. So a 2-sample t-test is when you have two groups. The way a 2-sample t-test looks is you have here a categorical variable on the x-axis. So you'll have down here like group 1, like group yes, and group no. And maybe this is people's grades. So you have a quantitative variable over here, like grade. And did you study is the categorical variable. So maybe people who study helps. It also matters how you study. This right here, yes. This right here would result in a very low p-value, given a decent sample size. That's because we have evidence of a difference between the groups. But when the groups get closer, the null hypothesis, which states, we're talking about like, did you study, did you not study, and do we see a difference between the groups and their grades? The null hypothesis would state that there is no difference. Kind of a basic way. Basic way of stating the null right here is no difference between the two means. I'm just writing an abbreviation. No difference between means. I'm going to disappear. And the alternative would be there is a difference. And this is the does not equals alternative. Classically written out, if we go classic stats, we're looking at mu1 for the top one. Mu1 minus mu2 is equal to 0. And just think about that. There's the two means and they have no difference. And the alternative is mu1 minus mu2 is not equal to 0, which states that there is a difference. Like when you subtract these two numbers, you do not see 0 as the difference, i.e. there is a difference. When you subtract these two numbers, you do see a difference, or you don't see a difference of 0. And this right here would be in line with the null hypothesis. So this looks like there is no difference, which means at this very moment, the p-value over here, p-value right now would be high. But if we start to see this right here where there is a difference, this looks more in line with the alternative hypothesis, which means we have evidence to reject the null, and now the p-value is going to be low. So p-value is low right here. This is unlikely to see given there is no difference. Could it just be that all the students who didn't study just did poorly by, wait for it, random chance? Maybe, but it's probably unlikely. We might see a p-value of like this right here, which basically means only about 4 in 10,000 times, only about 4 in 10,000 times would differences as extreme or more extreme than this occur by random chance, given there is no difference. So that's kind of some theoretical talk on a theoretical version of this problem, but let's go look at some jump output for it. So let's head over here to jump. Here, wait, watch this. There we go, okay. I want to go between it. All right, let's do a jump output on this. And so let's compare the blood pressure. Maybe I'm really concerned about blood pressure of people. Let's compare the blood pressure of older people and younger people. And when you think about the way I'm lining this up right here, you're comparing the two groups. You've got older and younger, which is a categorical variable, and you've got blood pressure, which is quantitative. So we're doing the 2-sample t-test here by comparing these variables, a categorical variable and looking at a quantitative y. So we're going to go to Analyze, Fit y by x. This is where we go to do the 2-sample t-test. And under the 2-sample t-test, the x does someone's age group explain someone's blood pressure. That's the variable we're interested in. The y, does someone have a certain blood pressure? Maybe it's their age group that explains it. So let's go ahead and take a look at this. And here we are. Interestingly enough, there might be a difference between the means, but there's definitely a difference between the variation. The young people are the ones with the really low blood pressure, and that's kind of weird. Kind of weird right there. Now, we do have our conditions for this. Condition 1 does not mention the project, but we do want these individuals to be randomly sampled. Condition 2 is they're less than 10% of all individuals. If this is this is a women's data set because it's got a bunch of variables in it from the Pima tribe. This is the Pima data set. And it probably is less than 10% of the individuals, I assume. And last condition right here, we have two more conditions. Random, 10%, and then we have nearly normal. Is the data nearly normal? Oof, it's a tough one. We're talking about conditions here for the test. Blood pressure. Let's look at it. Yeah, there's a little bit of outliers. Mostly nearly normal, but we have a large sample size, especially for the bottom group. With the larger sample sizes, the bottom group, I'm doing gender and GPA would, gender, great job, Emmy, right there. Excellent work. So do we use all the data? You don't take a subset. Great question right there, Kendall. Sorry, Kendall, it took me a second to see that. You don't take a subset, you use all the data. And this looks mostly nearly normal. You don't have to check these conditions. We're just kind of reviewing while we do this too to talk about, because this is the chapter we're covering right now, so it's good review. And the last condition here is their independent means, and the older group and the younger group, the means for those groups would be independent of each other. Like the older people's blood pressure will not have influence on the younger people's blood pressure. Like you're like, oh, my blood pressure's high. It's like, well, someone else is not going to be influenced by that. Yep, 100% recorded. You can review. You can even rewind live. Emmy, check it out on the bottom of the screen right here. If you click to the little, now make sure to come back forward. You can click the live button. But if you're watching this right now, you can actually like pause this video live. That's why I love this more than Zoom, is because right now you can hit spacebar on your computer and you'll pause me. You're like, wait a minute, you're going too fast, Brian. Pause that screen. You just pause the screen live. And so you can rewind live. You can pause the screen. That's why I love this more than Zoom. Sorry, Zoom. Haha. Yeah, no, it's that's why I love doing this stuff on YouTube. It's a lot of fun, and then I like the interaction we get here also. And I just did the t-test right there for those wondering in the background. And so keep asking those questions. We do see a difference, a rather large difference here between the groups. There's a difference in blood pressure of 8.5, and it is, let me look here, younger minus older. So older has higher blood pressure. The older group has slightly higher blood pressure by about 8.5. Why is it not selecting? Oh, it's just those points are all grouped up. The older group has higher blood pressure because younger minus older, it's like 80 minus 88 is -8. So the older has to be the higher mean of the two. We see here the standard error of the difference, which is the bottom portion of the equation. We did a problem similar to this a second ago. Do I still have it up? Yep. This is the standard error right here. This is the difference. So if you notice here in yellow is the difference and in blue is the standard error. This is the same output you see right here, where this is the difference between the two. That is the mathematical difference. This is a difference of -7. This is a difference of -8.5, older minus younger. And then the standard error right here is the bottom, which is this equation right here. This is our confidence interval for the difference. And yeah, but it does not contain 0. It's hard to see that negative. It does not contain 0. And also we reject the value of 0. We believe we're 95% confident the true difference between the blood pressure of the older and the younger group is contained in the interval -5.8 to -11.3, where the younger group is expected to have lower blood pressure. And yep. And we reject that there is not a difference. We have evidence there is a difference. And that's what I was testing right here. I was testing to see, do they have the same average blood pressure? And does that just make sense that we're pretty confident that younger people, there's a difference between younger and older people's blood pressure, and that older people's blood pressure looks to be about 8.5 higher than, does anyone do nursing or anything like that? Does that make sense to you that we have evidence that there is a difference between the blood pressure of younger and older people, and we believe that younger people have lower blood pressure? We have evidence of a difference. We can also say there's evidence that younger people's blood pressure is lower. We're doing the does not equals for this one, but we could look at this test right here and say we have evidence that younger people's blood pressure is less than older people's. Remember, low p-value means evidence for the alternative. So this is the less than alternative. This is the does not equals alternative right here. So if anyone's watching this in the future and you do medical stuff, you're like, yeah, that makes sense that younger people have lower blood pressure. So that is some good stuff right there. That is valid. We are doing some earth-shattering statistics right here by saying younger people have lower blood pressure, but we have confirmed that with statistics right here. Statistically speaking, there is evidence that younger people have lower blood pressure than older people, especially from this group. We have good evidence to believe that claim, and that's because the p-value is low. We reject the null that there is not a difference. We have evidence that there is a difference, and if we look at the alternative for the less than, we do have evidence for that. Let's hop here. I think there was a question on quiz 19 or homework 19. Let's go check that out. And I think we have an open floor on questions after this. So whatever you're working on, let me know that question. So, you know what? I'm going to change music. It is Statoil and Office Hours. Some 80s music now. And let's go in here. And the question was Question 4, homework 19. Question 4, homework 19. Dealing with those new My Pearson colors. Not used to it. My Pearson, how dare you? I'm going to demand the old My Pearson back. Say, we will not use My Pearson if they keep the colors the same. Question number 4. It's a good jump one. Let's go take a look. And here we go. Let's take a look at some chi-squared My Pearson. Homework 4, question 4. Homework 19, question 4. So this one right here is political affiliation and gender. So we have here male, female, Democrat, Republican, independent. Now, we don't do the chi-squared test of homogeneity. We do the chi-squared test of independence. And the way to think about the null hypothesis for this is we just put the word independent between these. So let's just say you were to go here, taking a little screenshot, and let's zoom in on this. The null hypothesis is easy to remember for these two because all we do is write the word in here. Independent. So the null hypothesis is that somebody's gender is independent of their political affiliation, which means it's not connected. Someone says, I'm a Democrat, and you say, okay. That's independent. But if it's not independent, someone says, I'm a Democrat, and you say, you're probably just have some sort of connection to it. So we are testing this right here. Null hypothesis being, let's write HO for null hypothesis. The null hypothesis states, that's how this is read, that gender is independent of political affiliation. That is the null hypothesis, which is just kind of a starting belief. The alternative hypothesis right here, we put a little A here for sub A, I said. Yeah, listen to me. Good. Great job. Is not independent. You could say is dependent. I like to do not because it's a complement. So gender is independent of political affiliation. They're just not related. And if you know someone's gender, it would tell you nothing about the political affiliation. Gender is not independent. That doesn't mean if you know someone's gender, you know their political affiliation, but it might mean they're more likely. You could think about how things are affiliated with political affiliation, especially states in the United States. If you know someone, I'm not saying they would be this, but if you know someone like from Texas, you might say, you might be more likely to be conservative. If you know someone from like New York, you might say, they're more likely to be liberal. But then you might say, what about upstate, downstate New York? Was the one-way analysis graph we did just the two sample? Correct. Yeah, that was the two sample we just did. Great job, Emmy, right there. That was the two sample T we were doing for the project. And upstate, downstate New York are very different. So if you know someone's from New York City, then that might be associated or not independent of their political affiliation. If you know someone's from upstate New York, I got my New York shirt on today because I'm from New York. So if you know someone's from upstate New York, they might be more likely to be conservative. But it doesn't mean they are that. It's just that it's not independent. It's like my friends from California. You might be like, you might assume something, but don't assume things. Statistics is about trends. Don't assume things. Yep, you'll screenshot. If you want to send it to me and I can take a look and make sure it's all right. But that's what we mean by the idea of not independent and independent. If something's independent, it would give you no information about it. Like, my friend likes cheeseburgers. And you'd be like, I know nothing about their political affiliation. My friend is from New York City. It doesn't say what political affiliation they are. Command Shift 4. Command Shift 4. Great question right there, Emmy. Command Shift 4. Hold Command Shift 4. Boom. And so we have that right there. Good stuff. And this is the chi-squared test of independence. Final check. Only get one check. So sometimes I try to mix it up on you here. We are getting some classic, like, political party is independent. of gender. Political party is not independent. Oh, no worries. Great questions. Keep asking those questions. Let me throw some 50 points out here. Keep asking those questions. You're here. You're asking questions. That's the way it goes. Excellent work right there. And sometimes we say that this means that they're associated. This means they're not associated. This means they are associated. Like to say two things are independent means they have no association. And not independent also means dependent. It's important to know a few different ways of phrasing this, just because there's different ways of phrasing it. Are the conditions for inference met? We need to have here, it's a random sample. We need a sample less than 10%, and we need count data. Now you might say, what is count data? All count data means is we have two categorical variables. You're asking a question like here, like someone's gender, that's a category. You're asking here somebody's political affiliation, that's a category. So it is count data. Count data literally means two categorical variables. It's like your QQ, but with two categorical variables, not too quantitative. Next, we have right here randomization. We'll assume randomization. Is it random? Maybe. Assume. I hate that. The expected cell frequency. Now, this is a tricky one. We're actually going to go ahead and solve this. The expected cell frequency. Let's go ahead and copy to clipboard. And this is where we are actually going to put it into JMP and solve a lot of the work. So we're copying it to the clipboard right now. We're going to go over to a new JMP data sheet by going to File, New Data Table. I'll pause right here. So when we go to File, New Data Table, we're going to open up a new JMP data sheet. Don't click inside of it. Don't click inside of it. Someone's going to click inside of it. And on the new JMP data sheet, you need to go to Edit, Paste with Column Names. That's when we copied it. We saw there was column names. So we're going to go to Edit, Paste with Column Names because there were column names to start. And now we've got it pasted right here. We could change this right now and call it gender. I double-clicked there. Does not matter if you change it. It's going to make it look nicer in a moment. But now we need to stack these columns. So I double-clicked and wrote gender right there and clicked OK. Let's go here to Tables. And let's make it full screen so you can see a little better. Tables and go to Stack. And then we're going to double-click everyone that's blue to stack them on top of each other. It's just going to take them and stack them on top of each other. And look at what we get. Here we are. This is what we want with two categorical variables, somebody's political label, we can call it that, and someone's gender, and then we have the counts. So these are just the counts, the frequencies. Now here's where the mistake happens. Listen carefully, watch out. Analyze. Fit Y by X. We're going to go here to gender. Does that explain someone's political label? But don't forget to put your data here in frequency. These are the counts, data, the frequency, the counts of observations, like how many individuals are in this group. If you don't put it there, everything will look kind of even and you won't have done it correctly. So let's go ahead and take a look, and there we go. It looks like males are a little more likely to be Republican. I think this drives people crazy right here because just in general in the US, we have colors that people associate. So we'll go blue on Democrat and we'll go red on Republican. And now that looks more like a little easier for people's eyes right there. You don't got to do these for yours. But you can see the males were more likely to be Republican. The females were more likely to be Democrat. When we finish the project, can you go over? Yeah. Did we? I think we just did those. We might have done those already. I mean, did we? I think we did those during office hours. I can send you the link to that. I think we did those today. So yeah, if you have more questions, let me know. I think we did those during office hours. So I might send you that link real quick right here but no, we can check that out. That was the bike route and then the children's sugar. And so yeah, we got, great questions. And we can do them again if you want. Let's go here and take a look. I'm clicking wrong buttons. This is where life gets a little bit easier. The expected cell count states that we want at least, and I'm removing stuff right now, we want at least 5 expected cell counts. Let's show how to find an expected cell count first. This is a formula you should know that will be on the test. To find an expected cell count, you need to go row total times column total over grand total. That formula for expected cell count is row total times column total over grand total equals expected cell count. So we want to actually check the smallest one is the best way to do it. So let's grab the smallest row total. They're both actually the same. Smallest column total, times them together, and then divide by the grand total. And so let's take a look right here. And that is the smallest expected cell count, 20.5. and it would be for individuals who are independent and males or females. So let's go take a look and see if that's what we're getting over here, because we can find all the answers by going to expected, and there's our 20.5. So we actually have all the answers here, and we meet the expected cell count condition. So we're good to go on the expected cell count. Good to go. Awesome stuff. Now the chi-squared test statistic, doing this by hand would take a while. The good news is the chi-squared test statistic is the sum of all cell chi-squareds. The cell chi-squareds are the observed minus expected squared over expected. So here we are with the cell chi-squareds. 3 plus 1 is 4. Plus 1.4 is about 5.4. Same thing here. And look down here. If we add it up correctly, we'd get 11.1. And this is the Pearson chi-squared test statistic, which is the sum of all of these cell chi-squareds right here. The cell chi-squareds, to show mathematically again, are the observed minus expected. So let's do this. Observed minus expected right here. Observed 28. That's how many we saw, the count. And then we minus off the expected, and that's 35. Now we square this, and we divide by the expected. And that's how we're getting that right there. Observed minus expected squared over expected is the value right here. Let's write that down so people can see it. That formula was, for the cell chi-squareds, observed minus expected squared over expected equals the cell chi-squared. And that is a cell chi-squared. And then to get the final chi-squared for all of this, we sum up all the cell chi-squareds. So it's the sum of the cell chi-squareds. So the sum of the cell chi-squareds is the Pearson chi-squared test statistic. Easy to remember because you're doing my Pearson. So is the Pearson chi-squared test statistic right there is the sum of all the individual cell chi-squareds. And that's got it right there. And we saw it's 11.149. 3 decimals, good to go. Nice work. Oh, it scares me. And then I believe it's a very small p-value, and we can check the p-value. I did it a little quickly there. P-value is 0.0038, and there it is right there. And we're using a 0.05 alpha, which means we reject the null. There is evidence to support the claim because we have a p-value that is lower than alpha. We reject the null. There is evidence to support the claim, and try not to make any errors. Oh, it's so scary. Emmy, did you want to do one of those, or do you want me to send you the link? Your call, Emmy. What would you like? Your call. Time for questions. Let's check it out. What sounds best to you, Emmy? Do you have one you want me to do, or do you want me to send you the links? What works best for you? Your call, your office hours, your call here. What shall we do? Get things ready. Let's take a look. Emmy's call on this, and we also have an open floor right now. Emmy's got first call if we do a question, or I put the link. What call is it? You'll see in the chat. Let's go right here. And let's take a look. I'll pull up where we did it today, but if Emily wants, we'll go through and do one. Feel free to ask. Let's see right here. I always try to do as many new things as possible. Be like, let's do as many things as we can. And here we are from today. Here we go. Here we go. Don't worry. I know everyone doesn't watch every office hours I do. I feel bad. We do all different stuff. And so here is the link for question 3. Let's put this in the chat right here. Question 3 from today, walking through it. There's question 3 in the chat, timestamped right there. And then we went here and did question 4. And let's take a look. Oh, there we go. And here is question 4 timestamped. And there we go. There's Brian and Brian. What's up, Brian? How do I look different? And it's like I'm having too much fun with this. Like, wow! I don't know how this happens. Is this an HD? It is an HD. Let's put on fast speed. Oh my gosh. What's going on? Open floor on questions. What questions are there? I'm gonna go eat some more lunch here in a moment. It's almost 5 p.m. Knoxville time. Oh my gosh. Let's go to Spice. What questions are there? We'll see if there's any last questions right here. It is your call. Let the music play here, and we'll see if there's any last questions. But I feel like people are doing all right on the project. We've covered a lot of details on the project. During office hours today, we went over the decision trees also. So check out office hours today for decision trees. We also did the 1 sample today. We did the 2 sample today. We did some homework today. Lots of good stuff right there. But please let me know if you're stuck. If some of the homework or the quizzes are not making sense, they're a little tricky during these last few ones. But you want to try to get as many great homework and quiz grades as you can. And if you get stuck, I can send you a video. I can answer some questions. But we got this. I'm going to go grab some more food. It's almost time for dinner. I'll see everyone later. Bye for now, everyone. Bye.